During this presentation, we will define the Doppler effect. We will discuss who discovered it and when it was discovered, and how we use it today. When a vehicle with a siren passes you, a noticeable drop in the pitch of the siren will be observed as the vehicle passes. This is an example of the Doppler effect. As the source moves closer to you, the wavelength shortens, giving a higher pitch. As the source moves further away, the wavelength becomes longer, giving a lower pitch. Doppler is defined by the increase or decrease of the frequency of waves due to the relative motion between the source of the wave and its receiver. For sound in particular, we use this equation. It is the Doppler frequency equals the frequency of the source multiplied by the speed of the wave added to the speed of the detector, which can be positive or negative, divided by the speed of the wave subtracted by the speed of the source, which also can be positive or negative.
Spectral Doppler is a form of ultrasound that uses Doppler shifts in order to display the velocity of blood flow at a certain point of time. From this display, we can figure out flow velocity, the direction of flow, the timing of the signal, and the intensity of the signal. A few specific measurements that can be obtained based on plot points or tracings that the sonographer uses are peak systolic velocity, end diastolic velocity, acceleration time, and max pressure gradients, among many others. The two main modalities of spectral Doppler are continuous wave Doppler and pulsed wave Doppler. Continuous wave Doppler uses two crystals inside of a transducer, one that constantly transmits a signal while the other constantly receives the signal. It is typically used for quantifying areas of high velocity blood flow, like what is found across the heart valves. Pulsed wave Doppler only has one crystal in the transducer that goes through periods of transmitting the beam to periods of receiving or listening to the beam. Pulse wave Doppler can be used in the heart, but typically it is used to evaluate arteries and veins.
Christian Andreas Doppler, Austrian mathematician and physicist, published a paper on the Doppler theory of light, which he titled On the Colored Light of the Double Stars of the Heavens in 1843. This paper was based on the theory of aberrations of light developed by Edmund Bradley, who was an 18th century British astronomer royal. Andreas Doppler established the principle of frequency shift and developed the formula for calculating the velocity from the shift. Doppler's theory that all stars emit a white light and the perceived color of the stars that we see relates directly to the Doppler shift phenomenon, where a red shift means the star is moving away from the viewer and a blue shift meant the star was moving towards the viewer, wasn't quite accurate. However, his theory of Doppler shift using sound waves ended up being correct, and that is what we based the Doppler shift as we know it today off of. The first applications of Doppler sonography were initiated in the 1950s. Shigeo Satomura from Japan developed the first Doppler ultrasound device for medical diagnostic purposes and reported recording various cardiac valvular movements. In 1960, he and another scientist, Kaneko, were the first to report the construction of the ultrasonic flow meter. Robert Rushmer and Dean Franklin of the University of Washington in Seattle, Washington, initiated the development of a prototype continuous wave Doppler device in 1959, and they reported blood flow assessment using the ultrasound Doppler frequency shift. They refined the device into a small portable machine and sent it out to clinical trials in the mid-1960s. The first pulsed wave Doppler equipment was developed by the same Seattle research team as the continuous wave equipment. Donald Baker, Dennis Watkins, and John Reed began working on this new project in 1966. They produced one of the first pulse wave Doppler devices. Other people who developed pulse wave devices were Wells of the United Kingdom and Perronneau of France. The images on the slide demonstrate Donald Baker showing off an early pulse Doppler device around 1975. The next image below that is the third version of the duplex scan head brought out in 1976, and it's explained under the picture that the plunger on the right moves in and out to adjust the range gating. The Seattle team also developed a duplex Doppler machine based on a mechanical sector scanning head where a single transducer crystal performed both imaging and Doppler functions on a time-sharing basis. The new duplex Doppler technique allowed the ultrasound operator to determine for the first time the target of the Doppler insonation. This development would prove extra importance and serve as a huge advantage with obstetric and gynecologic ultrasound applications, allowing the sonographer to more accurately target deep-range fetal circulation or female pelvic structures more accurately.
In the 160 years or so since Doppler first described the wave phenomenon that would cement his place in history, several practical applications of the Doppler effect have emerged to benefit society. In all of these applications, the same basic thing is happening. A stationary transmitter shoots waves at a moving object. The waves hit the object and bounce back. The transmitter, now a receiver, detects the frequency of the returned waves. Based on the amount of the Doppler shift, the speed of the object can now be determined. Let's look at a few specific examples: police radar, astronomy, and medical applications. Radio waves are sent out via the radar gun. The wave strikes the vehicle and bounces back towards the radar gun, measuring the frequency of the returning wave. Because the car is moving towards the gun, the frequency of the returning wave will be higher than the frequency of the wave initially transmitted by the gun. The faster the speed of the driver, the higher the frequency of the wave. The red shift and the blue shift describe how light changes as objects in space, such as stars or galaxies, move closer or farther away from us. The concept is key for charting the universe's expansion. The red shift implies the star is moving away from the observer and the waves are farther apart. The blue shift implies the star is moving towards the observer and the waves are becoming closer together. This illustration is excellent to further explain the red shift and the blue shift.
Doppler ultrasound is used to provide quantitative data that will help with the diagnosis of patients. Three key factors to observe in spectral Doppler imaging are the presence, direction, and velocity of blood flow. The presence of flow can be determined by a waveform or no waveform on the spectral display. Absence of waveforms mean that the sample gate was placed in the wrong spot, the angle of inclination is 90 degrees to that of blood flow, or the area being evaluated is completely occluded. The direction of the blood flow can be determined by which side of the baseline the waveforms show up on. Blood flowing towards the transducer will be above the baseline, whereas blood flow away from the transducer will appear below the baseline. The velocity can be determined by the height of the waveforms, above or below the baseline. Big waveforms demonstrate high velocity and small waveforms demonstrate low velocity, granted the controls are set up properly. The Doppler equation helps us better understand the variables that can affect the way the waveforms appear on a spectral display. Doppler signal strength is dependent on a few things. The higher the blood velocity, the higher the Doppler frequency. The ultrasound frequency depends on the transducer chosen. For heart studies, it is best to use a lower frequency transducer for penetration, but a higher frequency transducer should be chosen for more superficial structures. The higher the transducer frequency, the higher the Doppler frequency. After choosing a transducer, you can actually change the setting of frequency within the machine setup to optimize your spectral Doppler display. And of course, spectral Doppler is an angle-dependent modality. If the sample gate is not properly aligned to flow, the direction of flow becomes smaller. The beam angle should ideally be as parallel to flow as possible. Continuous wave is best performed with a blind probe with no 2D image display. Using this probe has distinct advantages such as a smaller footprint, which allows for more subtle manipulation, so alignment to possible stenotic jets can be better achieved. It operates at a low frequency, increasing sensitivity, and these probes have a high signal-to-noise ratio, which results in clearer spectral envelopes. Pulse wave is best performed with a 2D image as well as a spectral display. Since the placement of the sample gate is important with pulse wave, it is better to have a 2D image to work from, because pulse wave is displaying waveforms at a specific depth. Pulse wave is best suited for finding flow velocity and direction at a specific depth. The sample gate is placed in the center of a vessel or the tip of valve leaflets in cardiac scanning. The spectral display helps determine if there is disturbed flow in a vessel or the heart. However, if the area of interest being sampled has very high velocity, aliasing could occur. Aliasing is like a wraparound effect that the waveform has when the velocity gets too high. Or to put it in more technical terms, when the Nyquist limit is exceeded, which is based on the pulse repetition frequency, aliasing occurs. Continuous wave is mainly used to capture high velocity flow rates within the heart. Setting the sample gate along the heart valve, however, will show all flow velocities along the sample gate. Continuous flow is not prone to aliasing, making visualization and measurements easier to obtain. But by showing all velocities along the sample gate, it may make it more difficult to distinguish what or where to measure for quantitative data.
Long story short, it took years of research and many groups of people all around the world to develop the Doppler ultrasound that we know and use today. This image gives a very basic breakdown of the different types of Doppler ultrasound.
And now it's time for a quiz. Question 1. Name one modern-day use for Doppler that is not medically related. The correct answer would be police radar or astronomy. Question number 2. What does a redshift mean relative to the Doppler effect theory? The answer is A. Light or sound is moving away from the point of reference. Question number 3. How does continuous wave Doppler differ from pulse wave Doppler in ultrasound? The correct answer is continuous wave Doppler is a sound sent out continuously and sound received continuously, with no listening time in between sending and receiving.